Hello, everyone, and welcome to this session. In this session, we are going to build a complete machine learning model that predicts diabetes, starting from a raw spreadsheet of patient data all the way to a trained and evaluated and explainable model. This isn't just a coding walkthrough. My goal is for you to walk away understanding why each step happens, not just why code makes it happen, but that's the difference between copying a notebook and actually being able to do this yourself. We'll be using a data set from Kaggle, and we'll be using few libraries of Python like the Scikit Learn ecosystem. Yes, let's move ahead. So here's the roadmap for today's session. We will start with the data set itself, like what it contains and what each column means. Then we will explore it, which is where we'll uncover a couple of surprises hiding in the data. After that, we will clean it, train six different models side by side, evaluate them properly, and not just on accuracy but also finish by picking a winner and justifying that choice. So let's move further. Now, the first question. Before we touch any code, let's talk about why this problem is worth solving. Yes, like diabetes often develops silently. Some can carry risk factors like high glucose, high BMI, or a family history. Like for years before they are even ever formally diagnosed, they might be carrying all these health issues. So worldwide, over 422 million adults live with diabetes, and it's estimated that roughly one in two cases go undiagnosed. And guys, these are the real figures. Okay, that's the real opportunity here. A machine learning model isn't a replacement for a doctor, but yes, it's a screening layer. It's something that looks like a routine measurement and flags who might benefit from an actual diagnostic test earlier than they otherwise would have gone one. In technical terms, this is a binary classification problem. Given a patient's measurements, we are predicting outcome equals 0, meaning no diabetes, or outcome 1, meaning diabetic. Now, this is the big picture map of everything we are about to do today. Load the data, explore it, clean it, split and scale it, train multiple models, evaluate and compare them, and finally tune and finalize the winner. This isn't specific to diabetes prediction, by the way. Like almost every tabular machine learning project you will ever work on follows through roughly this same shape. Yeah. So pay attention to the pattern, not just the specific data set, because that pattern is the reusable part. Because every machine learning model needs these seven steps. Now let's meet our data set. This is the Pima Indians diabetes data set, a well-known public health data set originally collected by the National Institute of Diabetes and Digestive and Kidney Diseases, tracking diagnostic measurements for female patients of Pima Indian heritage. Right. And I have taken this data set from Kaggle, and it has around 768 patient records and 8 input features and one target column called outcome. So our task is simple to state that given a patient's 8 measurements, predict whether outcome equals 1 diabetic or 0, that is non-diabetic, because we have historically labeled outcomes to learn from, and this is what's called supervised learning, that is specifically for binary classification. Like supervised learning, it means the here the data set is labeled like for example, if you want to classify animals, then you can classify them like dog, cat. For that, for training the date, for training the model, you will be providing data set with labels, like with the picture of dog, there will be written dog, that yes, this is the dog, this is the cat, and in this way it works. That is called supervised learning. Let's have a look on dataset. So this is our dataset where the features are pregnancies, glucose, blood pressure, skin thickening, insulin, BMI, diabetes, age, out. So you can see 769 records we have. Now let's get back to our slide. Yeah, so as we saw in our data set, here are all 8 features we'll be working with. Like most of them are self-explanatory clinical measurements, that is number of pregnancies, blood pressure, skin thickness, age, and so on. We just saw everything in our data set. Two are worth calling out specifically. The first is diabetes pedigree function. It is a computed score that reflects family history and genetic predisposition to diabetes. And it's not a raw measurement, it's derived one. And the second one is glucose. That is a plasma glucose concentration from a 2-hour oral glucose tolerance test that turns out to be by far our single strongest predictor. And we will see exactly why a little later. Okay. Now, now let's have a look how our code will be looking like. Then I'll be giving you a live demo too. So first we load the CSV file with pandas, and then we check its shape and take a look at the first few rows. Okay, like running this code, we will be getting that 768 rows and 9 columns are there. That is df dot shape. Okay, and df dot head means you will be getting first 5 rows, and like here's where it gets interesting. Every column technically reports no missing values, but that's misleading. When we look at describe more closely, several columns show a minimum value or exactly zero, like for glucose, for BMI, for blood pressure, and that's not medically possible, right? So nobody has a blood glucose reading of zero while they are arrived. Yes. So even though Panda says nothing is missing, the data is quietly lying to us. That's exactly what we are going to dig into next. Before fixing anything, let's understand our target variable. Out of 768 patients, 500 about, that is uh, 65% are non-diabetic, and 268 patients, that is about 35%, are diabetic. This is a moderate imbalance, not extreme like 99 to 1, but enough that it matters. Here's why. A lazy model that just predicts non-diabetic for every single patient would already score 65% accuracy while being completely useless in practice. That's the exact reason we won't be judging our models on accuracy alone later in this session. Okay, so this is the pie chart you can see where 500 patients are non-diabetic and 260 patients are diabetic. Non-diabetic is shown by 0 and diabetic is shown by 1. Why we use 0 and 1? Because this is a binary classification. In binary, we use 0 and 1. Okay. Now, let's quantify that 0 problem we spotted earlier. In this data set, a value of 0 in glucose, blood pressure, skin thickness, insulin, or BMI isn't a real measurement. It means the value was simply never recorded, right? Now look at these numbers. Insulin is missing in 48.7% of rows. Yes, you can see insulin is missing. This is the graph. Now, that is essentially half the data set, right? And skin thickness is missing in almost 30% of the data set. Now, compare that to glucose and BMI, which are only missing in about 1% of cases. This is one of the most important findings in the whole project, and it's the kind of thing that separates a good analysis from a careless one. If we trained a model on this data as is, training these zeros as real measurements, we would be teaching it complete nonsense for almost half our insulin values. Yes? So we should resolve this before training our model. Yeah? Now that we know the data has some issues, let's see which features actually carry a signal about diabetes. Like this chart shows the correlation of each feature with our target and outcome. Glucose comes out only top by a wide margin at 0.47. Yes, you can see the correlation of each feature with outcome, that is 0 to 1 scale. Higher equals to stronger relationship. So here is our scale 0, 0.05, 0.1, 0.15, 0.2, 0.25, 0.3, 0.35, 0.4, 0.45, and 0.5. Yes, here we can see glucose is 0.47. That lines up perfectly with the medical reality that diabetes is literally diagnosed based on blood glucose levels. BMI and age follow behind it. Yes, you can see BMI and then age. And then comes pregnancies, then diabetes pedigree function, then insulin, then skin thickness, and then the last one, that is blood pressure. Now, as you noticed, blood pressure and skin thickness sit at the very bottom, barely correlating at all. That's not a coincidence. Those are the same two columns with the worst missing data problem from the last slide. That is why heavy imputation dilutes a feature's real signal, and we are seeing that play out directly here. Okay, so how do we actually fix this? Our approach has three steps. Okay, first, we flag the fakes. That is, we explicitly replace every zero on in those five problem columns with a proper missing marker using NumPy's NaN function. Yeah. Second, we group by outcome. We split patients into diabetic and non-diabetic groups because their typical values genuinely differ. Glucose runs higher in diabetics even among the real valid measurements. Filling with one dataset wide number would blur that difference. Third, we fill each group's missing values using that group's own median, not the mean. Now, why median? Because columns like insulin have extreme outliers, and some patients show insulin values over 800, and a mean average would get dragged off center by those extremes. The median resists that distortion. Okay. So let's move further. And this is the code, how it will be looking like. Yeah. Now, two more steps before we can train anything. That is, first, splitting the data. Why we need to split this data? Yes, for training purpose. Yeah, for training and testing purpose, we split the data. We reserve 80% of the data, that is 614 rows, according to this data set, for training and hold back 20%, that is 154 rows, purely for testing. We use something called stratified splitting, which keeps the same 65 to 35 diabetic ratio in both the training and test sets. So, our test set is a fair, representative sample and not a fluke. Second, scaling the features. Glucose ranges from roughly 0 to 200, while diabetes pedigree function ranges from about 0 to 2.5. Without scaling, models that measures distance between data points like k nearest neighbors or SVM would let glucose completely dominate purely because its numbers are bigger, not because it's actual more important. Yes. Now here we use something called StandardScaler, which rescales every feature to have mean of 0 and a standard deviation of 1. One subtle but important detail. We feed the scaler only on the training data, then just apply that same scaling to the test data. If we let the scaler learn from the test set 2, we would be leaking information and making our evaluation look better than it really is. Yes? Now, this is the code that looks like during training and testing splitting. Now, the fun part is training models. Instead of guessing which algorithm will work best, we are going to train six different ones on the exact same data. Yes? And let evidence decide which one is the best. First, logistic regression. It is the simple and interpretable baseline that draws a straight decision boundary. Second, k nearest neighbors. It classifies a patient based on its closest neighbors in the data. Okay. Third, SVM, that is support vector machine. It finds a flexible boundary between the two classes that maximizes the margin between classes. Fourth, decision tree. It learns a series of if-else splits, easy to visualize and prone to overfitting. Fifth, random forest. It is an ensemble of many decision trees voting together, and it is used for stability. Okay. And the last, sixth, that is gradient boosting. It builds trees one after another, with each new tree specifically correcting the mistake of the one before it. We will compare all six fairly on the same held out test set. Now, before looking at results, we need to agree on how we are actually going to measure success because accuracy alone isn't enough here, as we discussed a few slides back. Accuracy is the percentage of all predictions that were correct, but it's misleading on imbalanced data, right? So, precision tells us of everyone we predicted as diabetic, how many actually were, and recall tells us the opposite, that is, of everyone who's actually diabetic, how many did we catch? So here, recall is the most important metric as it shows us how many we actually caught. And if a single one misses, then it's like a blunder. Yeah. F1 score balances precision and recall into one number, and ROC AUC measures how well the model ranks risk across every possible decision threshold, not just the default cutoff. Okay, now I want to highlight recall specifically because in a healthcare screening context, missing a true diabetic, that is a false negative, delays real treatment. That's a far more costly mistake than one extra false alarm. So, recall gets the most weight in how we judge these models. And yes, ROC AUC stands for Receiver Operating Characteristic and Area Under the Curve. Yes, let's move further. These are the actual real results. I have first run the model, like it was taking a lot time. So I'll be showing you the Jupyter notebook of the model because this was like it took a lot time for training the model. Like it was around half an hour. So I just prepared it earlier. So these are the real findings. Okay. So we are looking at ROC AUC for all six models that are sorted from weakest to strongest. The weakest one is decision tree. Yeah. So decision tree comes in lowest, that is at approx 0.787, that is a single tree and is prone to overfitting one specific path through the data. And then logistic regression, KNN, and SVM sit in the middle. And at the top, clearly separated from the rest, are our two ensemble methods, that is random forest at 0.945 and the winner gradient boosting, that is at 0.957. Both ensembles combine many weaker models into something stronger and more stable. And that shows up directly in these numbers. Now, let's zoom into our winning model, that is gradient boosting, and look at exactly where it succeeds and fails on the 154 patient test set. Out of 100 patients who are truly non-diabetic, the model correctly cleared 91 and raised 9 false alarms. Out of 54 patients who are truly diabetic, it correctly caught 45 and missed 9. So, recall equals to 83.3% and precision equals to 83.3%. Now, those 9 missed diabetics, the false negatives in red, are the numbers that matters more in a healthcare context, right? That's 9 real patients the model failed to flag in a real deployment. We would want to push this number down further, possibly by adjusting the decision threshold rather than just using the default 50 to 50 cutoff. Now here you can see this is the confusion matrix where we have the column called actual diabetes and a row called predicted diabetes. And here we have divided it into four parts, that is true negative, false positive, false negative, and true positive. True negative means correctly said, that is no diabetes. False positive means wrongly flagged as diabetic patient. False negative means missed a diabetic patient and this is a costliest error. Okay. And true positive means correctly caught that the patient is diabetic. Now let's talk about how to actually read this ROC curve since it's one of the most useful and most commonly understood charts in classification. The curve traces the trade-off between catching diabetics, the true positive rate, and raising false alarms, that is the false positive rate, at every possible probability threshold at once, not just the default zero point 0.5 cutoff. The closer a curve hugs the top left corner, the better the model is. Yes, the diagonal dashed line represents pure random guessing. An AUC of zero point 0.5, a perfect classifier, would score an AUC of 1. Our best model gradient boosting scores 0.957. That is very close to that ceiling. Yes? Now that we know gradient boosting is our strongest model, can we make it even better? That's what hyperparameter tuning is for. Every model has settings that aren't learned from the data itself, like how many trees to build or how deep each tree is allowed to grow. Grid Search CV automates the search. It tries every combination of these settings and keeps whichever performs best. The key idea underneath this fivefold cross validation for every combination, the training data gets split 5 different ways, trained and scored 5 times, then averaged. So, the best combination isn't just something that got lucky on one particular split. One practical lesson I want to flag here is because it's an easy mistake to make, always tune the model that already won your comparison. Tuning a runner up, even very thoroughly, usually can't beat a stronger model left at its default. Yes, now beyond just making precisions, like beyond just making predictions, tree based models like ours can also tell us which features they leaned on the most. This builds trust, which matters a lot for a healthcare facing product that might need to justify its predictions to doctors or even regulators down the line. And reassuringly, glucose and BMI dominate this chart. The exact same two features that stood out in our correlation analysis several slides ago, and the same two a doctor would check first in a real clinic. That consistency between our statistical analysis and the model's actual behavior is a good sign. It's learned something medically sensible, not just noise. A trained model sitting only inside a notebook isn't very useful on its own. So the last technical step is saving it to disk using Joblib. That is, along with the scaler it depends on. Both files need to travel together. because any brand new patient's data has to go through that exact same scaling before the model can use it correctly. From here, wrapping this in a small flask or a fast API endpoint or a simple Streamlit interface turns this from a notebook into something a non technical reviewer, that is, a hiring manager or a startup founder, can actually click through and test for themselves. Yes, let's move further. So let's bring all this together. Our winning model here is gradient boosting with a ROC AUC of 0.957, a recall of 83.3%, and an overall accuracy of 88.3%. It wins for a few concrete reasons. It captures nonlinear interactions. For example, high glucose combined with high BMI compounds risk in a way a straight line simply can't represent. It builds trees sequentially, with each new tree specifically correcting the mistakes of the one before it, which sharpens its performance beyond a plain random forest. And it comes with built-in feature importance, which supports explainability in a healthcare context. We are keeping logistic regression in the conversation too, as an interpretable baseline, that is, a real healthcare startup might value that transparency even when its raw performance numbers are lower. Before we wrap up, here are 6 habits I want you to carry into your next project, not just this one. Yes? First, zero scan lie. That is, always investigate suspicious values before trusting a dataset that looks clean on the surface. Second, accuracy isn't enough. On imbalanced data, recall and ROC AUC tell a much true story. Compare fairly. Train every candidate model on the identical split and the identical scaling. Fourth, tune the winner, not a runner up. Fifth, explainability counts. That is, especially anywhere trust matters. Yes? And the last, that is sixth, save what you need. That is, your pre processing, like the scaler, is a part of the deliverable, not just the model itself. Now let's see our code on the Colab. So I've already prepared for you. Yeah, so let's start. Now here import pandas, numpy, matplotlib, and c1 are the libraries used for data handling. Like pandas is used for data handling, and numpy is a numerical library, and matplotlib and c1 are for plotting. So matplotlib is used for base plots, and c1 is used for styled statistical plots. Okay. And the rest of the libraries you can see it pulls in data splitting, tuning tools, and the scaler, and all 6 model classes you will train. Every metric function you will need to judge them, and here import Joblib. That is, Joblib is to save the final model to your disk. Okay, so this is what we can uh, interpret from this cell. Next, see, I have uploaded my data set over here. You can anytime open your data set and just check it over here. Okay, let's just close it. Now let's come back to our, yeah, this is our cell 2. These are called cells, okay, where I have been loading my data. So here pd.read CSV is reads the CSV from Colab folder. Yes, it should be in your Colab only, okay. Otherwise, it won't be reading. If you give any path, it won't be able to read the file. Okay. Into a data frame called DF. DF stands for data frame. And I have written print df dot shape that prints the rows and columns, that how many rows are there and columns are there in our data set. That is 768 rows and 9 columns. And df dot head prints the first 5 rows. Okay. And as you can see, it has printed the first 5 rows. So it confirms the column names, that is pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, diabetes, pedigree function, age, and outcome. Yeah. And now let's go to cell 3. Okay. This df.info prints each column's name, how many null values it has, and its data type. Okay. So all 9 columns show 768 non-null, meaning Panda sees no technically missing values. Okay. And D type means it shows data type. That is, here we can see float 64. There are two values. For int 64, there are seven values. Okay. And two decimal columns are there. That is BMI and diabetes pedigree function, and seven are whole number columns. Okay, this is the trap, that nothing looks like missing here, even though, as you will see 2 cells later, a lot of these valid numbers are actually zeros standing in for missing data. Okay, next is our cell 4, where I have typed df.describe. It means it computes count, mean, standard deviation. Uh, okay, mean minimum 25%, 50%, 75%, and max. Yes, for every numeric column. Now, here you can see, let's say glucose. In glucose, minimum is shown 0, skin thickness 0, insulin minimum 0, BMI minimum 0. Same problem. So outcome, what will be there? Mean equals to 0.348. Yes. Since outcome is only 0 or 1, the mean directly tells you 34.8% of 768 patients are diabetic. Yes. Insulin max equals to 846. You can see insulin max 846 versus mean equals to 79 point, if we round off, we can say 79.8. That is a huge spread, meaning heavy right skew outliers. This cell is what first proves the zero as missing value problem, before the code explicitly counts it. Yes? Now let's move further. Df outcome dot value counts it uh, it counts how many rows have each unique value outcome. Okay, like 0 के लिए there is 500 count, and for one that is diabetic patient it is 268. Okay, now let's move further. This is class balance chart. Okay, here SNS.count plot draws a bar per unique value in outcome, and bar height equals to count, and plot.title labels it so, and plot.show, that is plt.show, renders it. Okay, so you can see this is the count and outcome. What count do we have? 500 for non-diabetic patient and 268 for diabetic patient. Yes. Now let's find hidden missing values. Here, this line means is a list of the 5 columns where a 0 is biologically impossible. Okay, we are using 5 columns are glucose, blood pressure, skin thickness, insulin, and BMI. So this means that. Okay, and the loop goes column by column. For that we have used for loop. DFC equal to 0. It produces a column of true or false. Dot sum treats 2 as 1 and adds them up equals to count of zeros. Dot mean treats true or false as 1 and averages them equals to a proportion of zeros, and into 100 turns it into a percentage, and 1f formats to one decimal place. So this is the output what we got. Yes. Now this is the single most important diagnostic cell in the whole notebook, that it tells you exactly how much of each column is a fake zero or actually missing. Insulin is missing for 48.7% of patients, and skin thickness for 29.6%, meaning almost half your insulin values and a third of your skin thickness values will be filled in by imputation, not real measurements. That's a real limitation to state in this report. And heavy imputation on those 2 columns means predictions leaning on them are less trustworthy than ones leaning on glucose or BMI, which are only 0.7% and 1.4% missing. Now, this is our feature distribution. Here, df.hist is used to draw one histogram per numeric column in a grid, and bin equal to 20, it sets how many bars each histogram has, and fixed size sets the overall image size, and tight layout prevents subplot labels from overlapping. Okay, so you can see the histograms over here. Now let's see the output. First one is for pregnancies. It is right skewed, and most patients had 0 to 3 pregnancies and tail out to 17. Okay, see 17. Can you see? Next, glucose. Roughly, it is bell shaped around 100 to 125 with a small spike right at 0, the missing values. Blood pressure is also bell shaped around 70, you can see, with a visible spike at 0. Now, skin thickness, there is a huge spike at 0. Yes, you can see. Now, it is consistent with the 29.6% of missing values, plus a secondary bump around 20 to 30, you can see, for the real measurements. Next comes insulin, a massive spike at near 0, that is consistent with 48.7% missing values, and long right tail out to, you can see, till 800 plus, we can see it over here. Next is BMI. It is fairly normal bell curve around 30 to 35. Yes, and small spike at 0. Now, diabetes pedigree function. It's strongly right skewed and most values under zero point 0.5. Yes. Next is age. Here it is also right skewed histogram. Most patient in their 20s and 30s. The last one is the outcome. The two bar we can see 0 or 1. It is split from to 4. Okay. Next is correlation heat map. Here, df.core computes the Pearson correlation coefficient between every pair of numeric columns, ranges from -2 to +1. Here, all values are positive since none of these health features move in opposite directions. And SNS dot heat map, this one, colors grid by value. Anode equals to true prints the number in each cell. FMT equals to dot 2F rounds to 2 decimals, and CMAP equals to cool warm makes high values red and low values blue. Okay, so this is our heat map. Here you can see uh, glucose outcome is 0.47, that is strongest predictor by far, makes sense. And diabetes is diagnosed via glucose. Then comes BMI. You can see it is 0.29. Then age is 0.24. Then pregnancies is 0.22. Then diabetes pedigree function is 0.17. Insulin is 0.13. Blood pressure outcome is 0.07. Skin thickness is 0.07. Both are weak, consistent with them being the two most heavily imputed columns, which dilutes their signal. Also notice off target, that is pregnancies and age. Yes, this is pregnancies and age. It is 0.54, the strongest pair in the whole matrix outside the diagonal. Yeah, older women naturally had more chances to have been pregnant. Not a problem for tree models, but worth knowing. Now here we have plotted the outliers. These are called box plots. Here PLT dot subplots 2 comma 4 creates an empty 2 row into 4 column grid for 8 subplot axis returned as figure, the whole figure, and axis a 2D array of individual plot slots. And yes, axis dot flatten this uh, turns that 2D grid into a flat list of 8, so it can be paired one to one with columns. Yes. Now, across most panels like pregnancies, glucose, BMI, age, so on, one is diabetics box sits visibly higher than the zero box. You can see that. Okay. Diabetic box higher, 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 higher. Everywhere you can see. Confirming the correlation numbers above. Yes. Blood pressure and skin thickness show much overlapping boxes. Yes, you can see that. This is our blood pressure. See, overlapping boxes and skin thickness. It is due to their weak correlation to outcome. Now, in this cell, we'll be cleaning our data. Here we are using df.copy. It creates a copy and keeps our data as it is, our original data as it is. And after creating a copy, it starts cleaning the data. And here, like for each of the column problems, 5 column problems, dot replace 0 comma np dot nan turns every zero into proper missing marker. And this you can see dot group by outcome. This line splits rows into two groups, that is diabetic and non-diabetic, and computes the median of that column within each group separately and fills that group's missing values with its own group median, more accurate than one global median. Since let's take an example like diabetes tend to have higher glucose even among the true measurements. Okay. And dot seasonal dot sum counts remaining missing values per column as a sanity check. Now here you can see every column shows 0, confirms the imputation, filled every gap, nothing left missing. Let's come to our training and splitting data. Here x equals to every column except our outcome, that is the input, and y equals to just outcome, what we are predicting. Okay, here, what does this line mean? Train test split x comma y test size 0.2 and random state 42 and all. Let's see what does it mean. It means that it reserves 20% of the rows for testing, and random state equals to 42 makes the split reproducible every time you return it, and stratify equals to y forces both the train and test sets to keep the same diabetic ratio as the full data set. Next comes standard scaler. It creates a scalar object, and dot fit transform x train learns the mean or standard of each column from training data and rescales it in one step. Dot transform This dot transform x test applies the same learned scaling to test data. That is critical. It does not relearn from test data that would leak information. Yes. Now you can see the output. It shows a train shape, 614 columns and 8 row, and test shape is 154 comma 8, that is 614 plus 154, that is 768 rows and 8 columns each, and 9 original columns minus outcome. Now here we'll be training different models like logistic regression, KNN, SVM, decision tree, random forest, and gradient boosting. Here, each key is a display name, each value is an untrained model object. Okay, here max ITER equals to 1000 gives logistic regression enough optimization steps to converge. Okay, and probability equals to 2 on SVM makes it also output probabilities like needed for ROC AUC, not just hard labels. Okay, now for each of the 6 models, dot fit trains it on the training data, and dot predict gives 0 or 1 predictions on the test set. Dot predict probability gives the probability of being diabetic, that is column index 1 equals to the 1 class needed for ROC AUC, since that metric cares about ranking confidence, not just the final label. Okay, and now this statement, it retrains the model 5 more times on different slices of just the training data, each time holding out a different fifth to score, giving a more robust estimate, less dependent on one lucky or unlucky split. Okay, now this results dot append. Now it packages all 8 pieces of info for this model into a dictionary and appends it to the results list. Also stores the trained model object itself in fitted models keyed by name so it can be reused later without training. Okay, now this results DF. It turns the list of 6 dictionaries into a table, sorts rows by ROC AUC, highest to lowest and renumbers the row index from 0 to 5, that is reset index drop true, through away the old scrambled index from sorting. Here you can see model name, accuracy, precision, recall, F1 score, ROC AUC. CV ROC AUC mean CV ROC AUC standard. Okay, here you can see gradient boosting stands first and it tops every single column. That is best accuracy, best precision, recall, and F1 score, best ROC AUC, and a tight CV standard that is 0.012, meaning it's stable across folds, not a lucky split. Next, decision tree has the largest CV standard that is 0.032. You can see that. I have just rounded it off. Okay. A sign it's the latest stable most prone to overfitting single tree behavior. Third, logistic regression is the odd one out. It's bar based matrix. Accuracy is 0.708. Recall is 0.556 and loop weak, but its CV ROC is 0.866, is actually higher than several other models, meaning it ranks patients by risks reasonably well. It's just that the default zero point 0.5 probability cutoff isn't well calibrated for it on this imbalanced data. Okay, now let's compare the models using bar chart comparison. Blue one is for accuracy, orange for precision, green for recall, red for F1 score, and purple for ROCAs. Now, here you can see the graph plot. Yes, and this df.meld id wares. It is used to reshape the table from one row per model, the one column per metric, into one row per model metric pair. The long format, Seaborn needs to draw grouped bars. Okay. SNS bar plot draws one cluster of five colored bars per model, one color per metric. Yes. X ticks. It angles the model name labels so they don't overlap. Next is plt.legend BB box. It pushes the legend outside the plot area to the right so it doesn't cover any bars. Now you can see the output. Like it visually confirms the table that gradient boostings purple, that is ROC AUC bar is the tallest out of all 30 bars in the chart and its whole cluster sits highest overall. Logistic regression's cluster is shortest on the first four metrics, but its purple bar is still respectively tall relative to its own other bars. Now, this cell is for best model classification report and confusion matrix. So let's just see. Here, results df.iloc grabs the first row since the tables sorted best first. That's the winner. Okay. And model pulls just its name string. Okay. And here, fitted model's best name looks up the already trained model object by the name. Yes. Here we can see best model by ROC AUC on test gives us gradient boosting. This is the confusion matrix of gradient boosting. Now, PREDS equals to best model till here. It repredicts on the test set with the winning model. Then classification report prints, that is precision, recall, F1 score, support broken down per class, plus overall accuracy and averages. Okay, you can see this over here. Now here class 0, that is non-diabetic, 91% precision and recall. The model is very reliable at identifying healthy patients. Class 1, that is diabetic, 83% is precision and 83% is recall. And since it's the harder minority class with fewer examples, that is 54 versus 100 in the test set, and the noisier imputed features, that is insulin especially. Now let's see this confusion matrix. It returns a 2 by 2 grid of counts, that is true negative, false positive, and false negative, true positive. Okay. The heat map visualizes it and with actual integer counts. That is, for that we have written FMT equals to D. So you can see the confusion matrix here. Out of 100 truly healthy patients, 91 were correctly cleared and 9 got false alarm, and out of and 54 were truly diabetic, and 45 were currently caught and 9 were missed. Okay, that is false negative. That the number that the number is the one to highlight in a health report, since missed diabetic is the costliest kind of error we can ever afford. Next, we will be plotting the ROC curves for all the models. Okay, it loops through every trained model again, like you can see. ROC curve y-test probab. It computes the false positive rate or true positive rate pair at every single possible probability threshold, returning arrays, that is FPR and TPR. The third return value is the threshold themselves unused here. Okay, this is FPR, TPR we have returned. And each model's curve is plotted with its AUC in the legend label. The dashboard diagonal represents a model with zero predictive skill, that is AUC equals to 0.5. Okay, for reference. So this is our output. The blue line is for logistic regression, orange for KNN, green for SVM, red for decision tree, purple for random forest, and brown for gradient boosting. And dash 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 line is for a random guess, that is 0.5 AUC. Now here you can see gradient boosting and random forest curves hug closest to the top left corner, matching their 0.957 and 0.945 AUCs, visually reconfirming the table. Now hyperparameter tuning. I have done this for random forest and as well as for gradient boosting both. Okay. Now here parameter grid lists values to try for each hyperparameter. That is, grid search CV will train or cross validate a model for every combination, that is 3 by 4 into 3 by 3 equals to 108 total. Like it's wrapped around you can say random forest classifier. Okay. And not gradient boosting. So this is the mismatch flagged earlier since your actual best model was gradient boosting. So and job equals to -1 and uses all available CPU cores to run this. The best param is the winning combination from the grid search, and best score is the average cross validation ROC AUC. So you can see the best CV ROC AUC value and test ROC AUC after tuning. Okay, it is a difference. This is 0.94 and this is 0.944. Okay, now tune model till here. It is the actual retrained model using the weaning params. That is not just the parameter themselves. It reevaluates it on the held out test set. Like you can see it over here. This is tuned random forest score and actually lower than our untuned gradient boosting, that is 0.957. That confirms the earlier point tuning. Okay. So similarly, I have done the same for uh, you can see for gradient boosting also. So after tuning, we get the following values. Now, this is the feature importance graph. We have already covered this in our slides. Yes. And this for Joblib for deploying, we have also covered this in our slides. Okay. So, yes, this brings us to the end of this session. Yeah, so that's a wrap up. You can download dataset from Kaggle, and this is exit the pipeline, that is load, explore, clean, split, and scale, train, evaluate, tune, explain, and save. Isn't specific to diabetes. The same shape applies to almost any tabular classification problem you will run into next. So thank you everyone. And if you have any queries, so you can reach out us at biotech@gmail.com.